Hey everyone, and welcome to another Explainer by Forge College. Today we're doing something honestly really cool together. We are taking what usually just looks like dry, boring terminal code, and we're decoding it into a highly visual, technical schematic. We're talking about building a minimal Solana vault, completely from the ground up. We are going to explore the exact constraints, the sizing, the math, and the logic that makes a digital bank run securely on the blockchain.
Now, just to set the stage a bit, this explainer is a hands-on component of our broader From EVM to SBM trek. If you were with us for the previous explainer, Designing Solana Vault State, you'll remember we spent a ton of time on the theoretical design, right? How to track shares, how to balance underlying tokens. Well, today, we're putting on our hard hats. It's time to anchor those theories into reality, so you feel completely grounded in this curriculum. We're going to build a runnable skeleton that actually works.
Okay, let's dive into this. Here is our master schematic for today. We'll start by drafting the blueprints, then pouring the foundation, setting up the deposit window, opening the withdrawal window, and finally, inspecting the security.
All right, step 1, drafting the vault blueprint and scaffolding the program.
So before you can build a physical bank, you actually need to set up your drafting table. In the Solana ecosystem, our digital drafting table is provided by the Anchor framework. To set it up, we use just one perfectly simple command, anchor init minimal vault-javascript. This one command lays down our bare bones directory structure. It generates our workspace, the test files, the core Rust program files. Basically, it gets all the mundane setup completely out of the way so we can focus strictly on the architecture of our vault. Moving right along to step 2, pouring the foundation and setting up our accounts. What's really fascinating here is how incredibly precise we have to be with these architectural schematics. We have 3 main structures we're dealing with. The vault account needs about 200 bytes to store authority public keys and the totals for assets and shares. The receipt mint needs exactly 82 bytes, and the vault underlying ATA, the associated token account, needs 165 bytes. Now you might be wondering, why do we care about exact byte sizes? Well, to avoid paying rent on the blockchain. If you pack enough Solana into an account to cover 2 years of rent, it becomes rent-exempt. Think of it as paying off the grumpy blockchain landlord in advance, so your vault is literally never evicted. But who actually owns and manages these accounts once they're created? Let me introduce you to the PDA, or Program-Derived Address. I like to personify the PDA as our vault's robotic bank manager. This manager doesn't have a private key that a human could, just lose or steal. Instead, it's deterministically generated by our program using a seed, like the word vault. This robot manager tirelessly and securely signs the minting documents and token transfers so humans don't have to. It is the ultimate incorruptible authority for our minimal vault. Step 3. Building the deposit window and minting shares. Let's step up to the teller window and see how this builds mathematically over time. The very first deposit into the vault is beautifully simple. It's a 1-to-1 ratio. You deposit 1,000 underlying tokens, you get 1,000 shares back. Easy, right? But once the vault actually has assets, every single subsequent deposit requires proportional math. The shares minted must equal the amount deposited multiplied by the total shares divided by the total underlying balance. This ensures that no matter how the value of the underlying assets fluctuates, every single user gets exactly the slice of the pie they deserve. So, the crucial point here is how we handle that proportional calculation in Rust without blowing up our program. And that brings us to this big number, 128. Specifically, the U128 data type. You see, when you multiply 2 normal 64-bit numbers together, like a deposit amount and a total share count, the intermediate result can be absolutely massive. If it exceeds the maximum size of a 64-bit integer, your program just crashes with an overflow error. It's a literal math explosion. By temporarily casting our variables to this heavy-duty U128 calculator during the multiplication and then casting back to 64-bit afterward, we completely eliminate that risk. All right, step 4, opening the withdrawal window and burning shares. The withdrawal math at the exit door of our vault is basically the exact inverse of the deposit math. The underlying tokens to return equals the shares burned multiplied by the total underlying divided by the total shares. But, just writing out the formula isn't enough. Our robot bank manager has to validate everything. The program has to verify the vault actually has sufficient underlying balance to pay out, and crucially, it must check that the total shares count is greater than 0. We have to prevent a devastating division by 0 error. Safety checks are exactly what separate a good blueprint from a collapsed building. Finally, step 5, inspecting vault security through incremental testing. Because let's be honest, A perfect blueprint is absolutely meaningless if the execution is flawed. The smartest way to test a complex system like this is to bring in the automated inspectors and do it incrementally. First, we test vault initialization in total isolation. Does it create the accounts? Yes. Next, the initial deposit. Does our one-to-one math work? Yes. Third, we test a non-initial deposit to verify that proportional UN28 math. And finally, we test the withdrawal. By isolating one behavior at a time, if something breaks, you know exactly which window of the bank has a shattered pane of glass. It dramatically speeds up debugging.
Let's actually look at the numbers from our local test validator. We start with an initial deposit of 1,000, which creates 1,000 shares. A second deposit of 500 calculates out to exactly 500 new shares. Then, a user withdraws 250 shares, and they get exactly 250 underlying tokens back. And this brilliantly illustrates how the vault states precisely match our expected assertions during local testing. Our basic logic is airtight.
And that brings us to our conclusion and key takeaways. We have successfully translated theory into a functional, secure code skeleton. Let's rapid-fire the golden rules of vault building that we derived directly from the practical constraints we uncovered today. Number 1, always use proportional arithmetic for everything after that first deposit. Number 2, use the wider U128 integer type for intermediate math to absolutely avoid overflow errors. Number 3, set your program-derived address as the deterministic mint authority, so it acts as that incorruptible robot manager. And number 4, keep your unit tests relentlessly focused and incremental.
Now, as we wrap up, I want to leave you with a provocative thought. With your minimal, secure vault now built and tested, how will you handle complex fee models and precision rounding edge cases when your real liquidity suddenly scales up to millions of dollars? Well, that is exactly what we will be tackling in the next explainer. Thank you so much for exploring this with me today on behalf of Forge College. If you want to dive deeper into this subject and explore a ton of other amazing Web3 topics, make sure you head over to forge.college. Keep building, keep learning, and I'll catch you in the next one.